So it's early. Maybe we can have questions before this time.
Does that reference a paper, or is that a...
Yes, 3 papers. At the end, there are the archive numbers. Actually, I can show you in case some people want to download them. Here. So these 3 papers. This one from September, October, and February this year. This is what I'll talk about. Right. I think there are some chairs we can bring on the aisles. There's some chairs here. If people want to bring some chairs on the side. And there's some free chairs in the front. If you bring some chairs, I think there's room on in the aisle. There's one seat here in front. There's one seat here in front. Uh-oh, more people coming. Okay, guys, we need to bring some chairs. We need to bring some chairs. Oh, there are chairs over there. We need to pass the chairs. Be careful. I don't know. I think it's faster by the back, but anyways, maybe less dangerous this way. Be careful.
We could also sit here.
We could have an extra chair. Wait, we can have some chairs here. It's not always this full. Aaron, there is some seats here. And Simon, if you want to come forward, there are some seats here.
This seat will probably give it.
Oh yeah, obviously this one doesn't work, but we can. There's a seat in the back.
Oh, I see.
I guess we're using all the chairs. Okay, so I'm gonna get started. So thanks for coming, and thanks for something that I've been thinking about for a while, and I feel that in the last few months we've made some really nice progress. There are some still really major challenges in front, but as you'll see, I believe that now something like backprop becomes more plausible than it used to be. from the biological point of view. But it may also give us some ideas for going beyond backprop, and I think that's interesting for the machine learning point of view. So try to bear that in mind, that this work really is trying to go in both directions to provide more inspiration for machine learning, but also suggest some higher level explanations for how sophisticated machine learning could take place in the brain, because right now we don't have a good theory of basically credit assignment in the middle of the brain, this horizon, as you can see. Right. So, so backprop in the last few years, which has turned out to be incredibly successful, maybe probably much more than people would have expected a few years ago, because it's so simple. And when I mean backprop, I really mean how to compute the gradients in hidden layers and also in recurrent nets. Then, of course, there's stochastic gradient descent, which uses that gradient. I would say that part is, for now, less mysterious, but getting the information about what hidden units should be doing is I think, a big challenge. One thing I'm interested in beyond this research is how to extend the ideas we learn from these kinds of studies to deal with credit assignment when the quantities in the middle, the hidden unit activations, are not continuous, but maybe discrete, stochastic, and things that we don't know how to apply backprop to. I see more people coming. I think there might be room if we can just bring more chairs from outside. There are some chairs in the labs we could bring in, maybe. All right. So what do we know about how to do credit assignment in sort of deep neural nets? So most people here know about backprop, and I guess many people don't know that things like Boltzmann machines are able to do a reasonable job, maybe not as good as backprop. We don't have an easy way of comparing, of telling what hidden units in a deep network should be doing. And it looks like the principles involved in backpropagation and in the form of stochastic relaxation we have in Boltzmann machines are very different. But one of the contributions of this work is to establish somehow interesting connections between these two approaches. And of course, hopefully that may inform us about how brains could do something like backprop, because the kind of computation we see in most machines is much more plausible in terms of biological implementation than the kinds of computations that we think are required for backprop. All right. So one of the starting point of this research is spike timing dependent plasticity, which is a view of what's going on in synapses, at least in some neurons and some systems. It seems to be used in at least this characteristic I'm going to tell you about it has been observed in various places in the brain. What does it say? It says that there's a relationship between the timing of spikes from the pre-synaptic spike to a post-synaptic spike and the weight change. So on the x-axis here, you see in this picture results from biological observations from the late 90s. You have the time difference between two spikes, the presynaptic and the postsynaptic. And here, the presynaptic comes before the postsynaptic, and the 0 is here. So here, the order is reversed. Post comes before pre. And what you see here is the relative weight change, so 100% means no change. And then these circles correspond to particular observations. And you see this funny curve, which basically says that the spikes have to be close enough, and that depending on the order, you get a different sign of the change. Yes.
Does this mean that like a single spike is going to change like double the weight?
No, this is after many repetitions.
Okay.
Yes. Otherwise, you wouldn't be able to measure that change. At least the changes are very tiny. So you have to repeat this many times before you see that kind of change. So the first paper, I showed at the beginning a list of 3 papers, recent ones, and the first one was essentially work done last summer, where we proposed to replicate the kind of observations that relate the spike timing difference and the weight change through a mechanism that seems to not require spikes. It is just based on the rates, the spiking rates of the neurons. And essentially, we studied weight update rules that are of this form. I'm going to explain the notation. So the synaptic weight relating pre-synaptic neuron J to post-synaptic neuron I, so from J to I, is proportional to a product, like in Hebbian updates. But on one hand, you have the pre-synaptic, this is the pre-synaptic firing rate. On the other hand, we have a rate of change of the post-synaptic activity. So either the post-synaptic firing rate, like here, or the post-synaptic voltage. So let me explain this notation here. So rho is the sigmoid, or the nonlinearity that produces the firing rate from some unbounded quantity, and that unbounded quantity is the S here. The S, would be something like the voltage potential, but integrated to average out the effect of spikes. The actual voltage potential goes up and down all the time because of the spikes. So this would be a kind of underlying smoother version of that that reflects the firing rate deterministically. And that S, we call it S because we consider here that it's the state of the neuron, and globally the state of the network is represented by this quantity, this real value quantity for all the neurons. So in both machines, the state is represented by a binary stochastic variable that says yes, no is firing, whereas here we have a continuous variable that's essentially corresponds to the firing rate, but it's a real value, unbounded real value one, which is more like the voltage potential. Okay, so that's my notation for now. If you have questions, please interrupt along the way. Okay. Yes, I've said that already. And now the happy coincidence is that this learning rule, when we run simulations, gives rise to a relationship between the spike timing and the weight change, which matches pretty well the biology. So when we run those simulations, we take the firing rates that we're getting through a leaky neuron integrator, so standard equation that I'll show you later. And we turn these firing rates into actual spikes randomly according to a Poisson process. So we replace the smooth deterministic quantities that are the firing rates and the states by these random quantities that go 0, 1, according to the probability given by the firing rates. Yes.
Is all of the biological data observational, or
yes.
Can they do causal stuff where they induce a spike and see what happens?
They always induce a spike. That's the way they do it. So that's they basically stimulate presynaptically and postsynaptically in order to achieve and then they measure how the presynaptic firing rate is converted into a change in voltage, and that's the weight, the synaptic weight.
I think they use a spike train.
Spike train, of course. You need a spike train, right? Yes, absolutely. So so it's kind of funny that this rate-based kind of formula seems to capture behavior that seems to require very precise timing. And in the paper, we give some kind of intuition that I can try to share briefly about why this happens. So imagine that x-axis here is time, and y-axis here is the postsynaptic state. So analogous to the essentially the firing rate, and we're going to gradually increase the post-synaptic firing rate. So the neuron that receives the inputs is getting more and more excited. Okay, so its firing rate increases. And while this is happening, we consider a particular spike on the pre-synaptic side happening at some point. But now, because the reason I'm doing this is the equation here has the temporal derivative of the post-synaptic activity. So I'm assuming that this S dot here is non-zero. If you say positive, so it's going up. So now, if you think about the STDP rule with the timing, we can think about what's happening. We have the presynaptic spike that's happening somewhere. But now the thing is, on the left side, so before, there's an asymmetry between what happens before and after, because the firing rate is now smaller before than after. And so because of that, you're going to be more likely to see spikes after than before. And they'll tend to be closer to the presynaptic spike. And so that kind of explains how you're going to be more likely to, depending on the sign here, you're going to be more likely to see the difference having a particular sign, this difference in timing, which is what the STDP observation is about. Okay, so now this was essentially the first paper. Question is, this is all nice, but it's still far from connecting to machine learning, right? How is that related to like doing gradient descent on some objective function, which is the kind of thing we like to do in machine learning because we understand what it means in terms of learning, and you know, this is the framework that has dominated machine learning for decades and works so well. All right, so let me give you first a kind of intuition that comes out of thinking about this update. So if you remember a little bit from backprop in regular neural nets, if you have the activity being roughly a linear combination, weighted combination of input firing rates, then DSI, DWIJ is going to be rho of SJ, right? So that part of the computation of the gradient is something we see in the update rule that we have proposed. So we have one part. So if that's DS DWIJ, then if we want this update to be something like stochastic gradient descent, we need the S dot to represent the derivative of some objective function with respect to S. Right. So that's a very intuitive thing. We're going to be trying to reach something like this. It's already telling us an interesting story that if we really want to go that route, then it's going to mean that the neuron's activity is changing in such a way as to reduce some error, say J, that we're making. This idea actually comes from Jeff Hinton in a talk he gave in 2007 at the first deep learning workshop. And basically, he had this insight, and he was so excited about it that he gave a talk which was something like, I know how the brain works. and I think this insight is very important. And so we're going to try to dig a bit deeper to come up with a mathematical mechanism that would give rise to something like this. Okay, so now you see a potential connection because, you know, how is that going to be true, right? But that's where we're going, right? So keep that in mind. Now, let's try to be a bit more precise about what we're going to be doing. We're going to be dealing with neurons that are a bit more like the ones we find in biology than the ones we typically use in artificial neural nets. So in artificial neural nets, we have these discrete steps, and the neuron instantaneously takes a value based on the weighted sum of its inputs, right? But that's not actually what happens in biological neurons. They slowly change. They have some inertia. And you can, and people in theoretical neuroscience have characterized that using differential equations. So they take the state, like in my case, the voltage or the firing rates, and they define differential equations that say, okay, so this is the rate at which, say, the state of the network changes, And it's going to be, this is going to be 1 over some time constant that decides how far this is, how fast this is moving, and then there's going to be something. And it's very convenient to write it as a difference of 2 terms. The reason I write it like this is because if this function R of S, which is basically the weighted input coming from the rest of the network, was fixed, then this differential equation would converge to S equals R of S, right? Because when is this converged? This is converged when S dot equals 0, when the derivative, the fixed point is when the derivative is 0. So when this is 0, then we have that the state is equal to this quantity, and that quantity would be the usual weighted sum of inputs, okay? Maybe there's some nonlinearities inside, like I had before. And so that's one way to see why this is interesting to write it like this. And it's also interesting to think about it in the light of the discussion in the previous slide, that the neurons are changing towards trying to do something better. That really, this is a kind of gradient descent. Right? You should recognize this is a kind of gradient descent. We take the new state is the old state plus some small quantity times something. So the something, the R of S minus S, must be, if this was gradient descent, must be the derivative of something, or minus the derivative of something. We're trying to go down some energy, say. All right, so this is an interpretation we're going to also stick to for the rest of the presentation. And if we define it like this, it means that there's going to be a relationship between the energy, the thing we're trying to minimize, and this function R, which essentially defines what the neurons are doing at each time step. Okay. And we'd like to find an energy function that's going to have the property that the R is roughly going to be the usual weighted sum with the bias or something. Now, when I saw these kinds of equations, I thought, gee, I've seen this R of S minus S thing before. And actually, it's something that came up in the work on autoencoders, denosing autoencoders, where we find that when we train denosing autoencoders with a reconstruction function S that essentially maps the old state S to a new state R of S, where R is like encode decode, right? So it's a bit different. We get that when we want to minimize reconstruction error, the R converges to the gradient of some energy. So this connection between the output of a neural net minus its input and some derivative is something that I had seen before, and seems to come out of things like autoencoders. This was kind of a interesting and happy coincidence. Right. So if we believe this energy connection, then what it entails, and that's again, that's not a new perspective, that what neurons do for a living is inference. That they're going down the energy. So what is inference in machine learning? It's the process by which the hidden units, for example, the latent variables, are changed towards configurations that correspond to high probability, given some constraints, given some observations, given some inputs. In the brain, we have some inputs, and then the hidden units, so basically most of the brain is changing to go into a configuration that is in agreement with what is being observed. And that's inference. And it's going to be iterative typically. And the simplest kind of iteration would be just some kind of gradient descent. That would be the deterministic kind of inference. You could easily make it stochastic, as I'll tell you later. And I haven't studied that very much in this work up to now. So now what kind of energy function would have the property that the corresponding R, so there's this connection, right, between the energy function and the R function. We would like to choose the energy function such that R, which is like minus dds, which is S minus dds, we would like R to correspond to our usual weighted sum. So actually, this question had been resolved a long time ago by Hupfield in the early 80s, and he proposed a pretty ugly energy function that would have this property. I happened to stumble onto something related, but not exactly the same, which is this energy function, which I find much nicer. It's just my sense of aesthetics. It's almost the same as the Boltzmann machine energy function, for those of you who know about Boltzmann machines. The difference is that the state variables now are these continuous state variables, and instead of having the binary units here, Si times Sj, we have the sigmoid or some kind of nonlinearity here for the two neurons that are connected to each other through a weight Wij. The rest is the same. Bias terms is usual, and of course, because we have continuous value things, we need some kind of containment term that we usually have in things like Boltzmann machines. And it turns out, of course, this S squared is precisely what we need to get the S here. When you take the first derivative, we're going to get the S, and then for the derivative of this guy's, well, you're going to get the usual B plus W times input, but multiplied element-wise by something kind of different from usual, which is the first derivative of the nonlinearity on the post-synaptic side. So, but it actually turns out that when you're interested in what happens around fixed points, or if you think about the dynamics more generally, this term isn't playing such an important role, except making sure that the activities stay in some bounded range, essentially. The S is going to stay in some range where the derivative is non-zero. Yes?
Can you assume that that function is monotonic?
A rho? Yes. I'm assuming that rho is monotonic increasing. Yes. So the actual rho that we use in our experiment is just what we call the hard sigmoid. This, like 0, 1, something like this. Pretty straightforward. Yeah.
I thought rho is supposed to represent the firing rate.
Yes, the output of rho is firing rate, so it's between 0 and 1.
And the state of the neuron is a real number?
Yes.
Okay.
Yes.
Okay.
And B is going to be threshold or minus threshold. Okay, so as I said earlier, we can take these kinds of equations and add noise. And now the inference is going to be sampling from a distribution. And if you add the right amount of noise, you get what's called Langevin MCMC. So the Langevin Monte Carlo Markov chain basically says I'm going to update my state to do a kind of gradient descent in the energy scaled by the amount of noise that I'm also adding. So I'm going to inject noise all the time. And so long as I scale my noise and my gradient appropriately, I'm sampling from a distribution that that has this energy function after a while, of course. But so this is just kind of a connection that needs to be strengthened. But for the rest of the talk here, I'm just going to consider the deterministic version of this, where I just ignore, I don't have noise. We can add noise in the experiments, and it seems to work as well, but we need to study that a lot more. Okay, so there's a thing about symmetry here. If you actually take the derivative of the energy function, so if you apply this equation to define R, you get actually this, which isn't exactly what we want, because you see in the energy function, when you take the derivative with respect to the Si or Sj, right? You're going to get a term for Si in both places when it's playing the role of the pre-synaptic side and when it's playing the role of the post-synaptic side. Because this thing is symmetric in rho of Si and rho of Sj, you're going to get two terms in the derivative. And that's going to give you Wij plus Wji. And if you have the 1/2, then it's going to be the average of the weight going in one direction and the weight going in the other direction. And that's kind of inconvenient because that doesn't look like what brains would do. Like, you would need to have neurons communicate with each other. Their synapses that are symmetrically connected would need to talk to each other to keep in sync. Anyway, so right now I'm going to kind of hide that under the rug and assume somehow that there's a mechanism that allows the weights to be symmetric. So I'm going to force Wij and Wji to be the same. And okay, so why is that a reasonable assumption?
You not just force one of them to be 0?
No, because I'm going to need the feedback connections, right? The feedback connections are going to be super important because they're going to be doing the job of backprop. Now, the good news about this apparently very strong assumption is that this kind of symmetry arises naturally. So there is some experimental evidence from training denoising autoencoder. So if the layers were trained, if each layer was trained as an autoencoder, and the weights are free to learn independently, but they somehow minimize the reconstruction error, then we find the weights to tend to converge towards the same value, the Wij and Wji. And there's also some theory, very recent, November the previous year, in 2015, that also suggests the same thing, that if you have a network with rectifier nonlinearities and you minimize a kind of reconstruction error, then the optimal solution is one where the weights going up and the weights going down are the transpose of each other.
We actually have a formal proof for that in a paper that appeared in AAAI 2016.
Which AAAI 2016? So which?
The conservativeness of autoencoders.
No, it's different.
Oh, okay, I'm mistaken then.
Yes, I've seen that paper. But Roland worked on this because I asked him, could you find a way to force the weights to be symmetric? But what's shown in the paper is different. But anyways, yeah, I know about that connection. And I think there is a connection, but it's not showing that. All right. So now the big meat of this talk is that if you take these kinds of recurrent networks with symmetric feedback connections and you set them around a fixed point, and then you start stimulating some of the units, that will create a perturbation that travels through the layers. And if you study those perturbations, they essentially will propagate gradient information just like a backprop would. Okay, so now let me, for pretty much the rest of the presentation, go into this a bit more in detail and see how it happens. So the setup is our state now is going to be divided into inputs, hidden, and outputs. And of course, the hidden themselves could be divided into different layers. And I'm going to assume a scenario which is very simplified, and again, this is just the first step towards trying to make a kind of biologically plausible backprop. The scenario I'm studying is a standard supervised learning scenario. So the X is going to be first given. The network then relaxes to a configuration where it likes the X. So it finds a fixed point of RS. Our RS is equal to S under the constraint that X is clamped to some values. And of course, that means H and Y take some values. And now we're going to take the values that are taken there by the Y as predictions for the actual observations of the Y. And then we're going to measure some error. So it could be squared error. The math is actually more general, thanks to Benjamin Sellier, who's not here, unfortunately. I think he's now on a plane to India or something. Yeah, he did a lot of good work with me on this. And one of his contributions is generalizing my initial math to deal with any kind of cost function. But for the sake of keeping ideas simple, you can imagine that we have a prediction cost, which is comparing the actual Y coming from the outside world with predicted Y, which is what the R function is, the reconstruction or prediction function for each neuron is where each neuron wants to go. So the output neurons want to go in some place, and we're comparing that with where they should have gone. Okay, and we're going to be interested in these perturbations now. So what's going to happen, I'm going to assume that the output neurons are going to receive an external input that's going to drive them towards minimizing that cost. And so they're going to change according to some quantity delta Y, which is the observed Y minus their the prediction which you got after the initial phase of relaxation, which we call the negative phase by analogy with Boltzmann machines. So in the negative phase, we get these configurations of the y's, and then they're going to start moving towards the actual observation. And they're going to start moving slowly because these are leaky integrated neurons. They follow these inertial, differential equations, and so this is going to be a gradual process in continuous time. And what I'm going to try to show later is that this small perturbation delta y here, because we have feedback connections, is going to unsettle these guys, right? So they were at a fixed point. So they were all happy with each other. And so they keep talking to each other. I'm happy with you. I'm happy with you. I'm happy with you. And then suddenly those guys start changing. They play a different game. And so these guys say, hey, what are you doing? Oh, I have to change 2 to be in agreement with you because of the feedback, and they keep looping with each other. And so these guys are going to change. And now we're going to have a delta H1. Now, because these guys are changing, they're not anymore in agreement with these guys. So these guys have to change as well. And so you'll see a wave of perturbations going from the sensors for the prediction back towards the lower layers. And now I'm going to try to convince you that these perturbations actually correspond to backprop.
So,
yeah.
Is there also a view that it's almost like you have an adversary that's sort of trying to play against the neurons in the hidden layer, and it's sort of trying to perturb it such that, I'm not sure, it just sort of occurred to me that maybe there's some sort of adversarial connection going on with this external signal.
I don't see the connection, but I'd be glad to discuss it eventually with you.
Okay.
I see it more like harmony. They're trying to, be happy together, and so they want to be happy with the new signal that comes from the outside. Yeah.
I have a question where if you want to show that these neurons have energy function, then, but if that's the goal, why does Wij and Wji has to be symmetry? Even if it's not symmetric, but if you can show that it has energy function, is that good enough?
So I think that it's possible to define other energy functions where you may not need that symmetry. Right? But that energy function is symmetric by its construction. So I think this is an open problem, and I don't have right now a complete solution to it. I have some clues that maybe it's not just it's a big issue, because we see that autoencoder reconstruction errors lead to symmetry.
Right. But also, if you consider untied autoencoders,
Yes.
and then maybe if you look at the Jacobian of the autoencoder,
Yes.
that itself is symmetric, and that itself shows that.
But that's not what we're trying to do here.
But
I know that the Jacobian is symmetric, so that's connected to your question. But it's not what we're trying to do here. We're trying to show that the Jacobian is the product of 2 Jacobians, which are symmetric.
But
And that's different.
But you wanted to show that because you wanted to show that it has energy function. These neurons have model energy functions.
No, I need to make the thing that I'm trying to do is to make sure that the neural computation, like the weighted sum, corresponds to the derivative of an energy function. That's what I'm trying to do. So the normal or some plausible neural computation has to arise out of some energy function. That's why designing the energy function isn't like something you can play with usually in machine learning, because we want at the end of the day that the updates we're getting correspond to some kind of inference in the energy function. And so there may be other solutions here. I mean, this is just the one we've studied.
One more very short question.
Yeah.
Just to make sure, you're talking about gradient descent in the space of ages, not in the space of weights.
That's right. This is inference. So it's in the state, in the space of the states, the h's and the y's.
It's just very easy to confuse.
Yes. So it's inference. It's not learning yet.
Yeah. Okay.
The end of the presentation will be converging to basically a conclusion that, oh, this is actually doing stochastic gradient descent on the prediction error with respect to the weights. But the intermediate stage of this analysis is, are we even doing inference? And what is the inference computing that may be useful for learning, because these gradients, backpropagated, is what we care about. So, okay, so what I'm going to do is I'm going to define a kind of modified energy function, which is the original energy function plus some penalty terms, which correspond to prediction error terms. So, so beta x and beta y are going to be some scalars, and cx and cy are the prediction errors on the inputs and the outputs. So this might be the square difference between the input units and the outside inputs, and this might be the square difference between the output units and the outside outputs from the targets. And so the idea is we're going to play with those betas to kind of emulate the supervised learning setup by setting beta x initially in the negative phase. I'm going to set beta x equals infinity. And so that's going to kind of clamp x. It's going to go very, very fast to x equals whatever, minimizes this cost. So x equals the observed input. And we're going to leave beta y equals 0. So initially, there's no constraint on the y. That's the negative phase. And then in the positive phase, I'm going to have basically beta y non-zero. So the f plus is f minus plus a term for the output error. And now x is still clamped, but I'm adding some pressure to move the output units towards our target. But I'm going to do it differently from what has been done in the literature in the past. So these kinds of ideas have been around in papers like Sebastian Sung's paper on contrasted hidden learning, or in Boltzmann machines and things like that, where we first clamp the input, then clamp the outputs, right? Here, I'm not going to clamp the outputs. I'm going to just give a little nudge on the output units towards the targets. And I'm going to do that by only requiring, making beta y small, epsilon, actually infinitesimally small. So we're just going to have a little push on the output units. And why am I doing this? And why do I think that it's okay to do that intuitively? It's because if you remember, I'm trying to get the derivative of the costs cy with respect to the hidden units, right? That's what backprop does. And as you remember from the chain rule and backprop, this basically goes in two stages. You have the derivative of the cost with respect to the outputs times the derivative of the outputs with respect to the hidden units. And so as far as the first term is concerned, the derivative of the cost with respect to the outputs, I don't need to drive the outputs to their target value. I just need to have that information, the gradient, d prediction error dy. I just need to have that delta y, right? I just need to get this quantity delta y into the system. I don't need to drive y hat directly to y. I just need to move the y's towards their observed value a little bit. And so I can do a positive phase trajectory, which just is going to be infinitesimal, right? It's going to be a trajectory, but it's going to be infinitesimal. It's very, very, very small trajectory by giving it as a target the output plus a little bit of what it needs to reduce the error towards the target, right? So just add delta y to y hat. And so my positive phase that I'm going to be defining is one where I'm going to choose a very small beta y, actually infinitesimal, positive. And so I don't need to do full inference on the to minimize the output prediction error. All right. So that's in line with this notion that I gave you before, that we're trying to set things up so that just the propagation of these perturbations gives rise to backprop. All right, now it's going to get a bit more mathy. So, either shut your eyes or try to pay attention. So the way I'm going to do this now, and here I have to give credit to Benjamin. I had a first proof of this, and he had a much nicer and more general proof. The way we're going to do this is we're going to think of this objective function. So our objective function basically is like this. We would like to do two things. We would like to consider the situation where the state is at the fixed point corresponding to the negative phase. So when we clamp the inputs and the system relaxes to some configuration. So that's the F minus. So the energy, the augmented energy in the negative phase, we would like this to be equal to 0. And that's going to be the case when the state is this negative phase value S minus. Right. So we would like to enforce this constraint that when the state is corresponding to the fixed point for the negative phase, the cost is minimized. So we do that with a simple, minimization under constraint with Lagrange coefficients. So we introduce these Lagrange coefficients. So here lambda is a vector, and we take the dot product of that with its derivatives. So for each of the constraints that come out of this this being equal to 0, we're going to have a coefficient. Right, so that defines a new sort of Lagrange objective that now depends on three quantities: the states, the weights, and the new coefficients lambda. Okay, and now we do the usual things we do with these animals. We consider the derivatives that we can set to 0. If we take the derivative with respect to s, what do we get? We get dc ds plus lambda times the second derivative of f minus with respect to s. So when this is equal to 0, we have a special value of lambda that's going to satisfy this equation, and I'm going to call this special value lambda star. Right? It's the lambda that corresponds to minimizing over s and maximizing over lambda, which is what the Lagrange thing is about. So we have this fixed this equation to be satisfied by lambda, and part of what I'm going to do next is trying to find, well, how do we find lambda star that satisfies these properties? Okay, now if we have these two equations satisfied, right? The derivative with respect to lambda gives us set that to 0, we get df ds equals 0. So that's basically saying, well, this is the negative phase, S minus is the negative phase fixed point. We know how to do the computation to reach that point. And we also have to satisfy this equation. And right now, we don't know how to find lambda that satisfies this equation. But if we had a way to find the lambda, so now we've optimized in S and lambda, we can do gradient descent on W, right? So that's what we will do. We will say at the S minus and lambda star, we're going to take a gradient step. So we're going to go down. The weights are going to change towards minus dl dw, and that's going to be the product. So that's just going to come out of looking at this equation and saying, okay, differentiate with respect to w. Where is w? So w, you have to understand here that s is it's not like in backprop where s is viewed as a function of w. S and w are variables, on equal footing here in this definition. So there's no w here. There's only w hidden in the energy function. So when I take the derivative with respect to w here, this term vanishes, and the only thing I get is the lambda, which has to be lambda star, times the second derivative of f with respect to both s, which we already have here, and w. Okay, so it's just differentiating this with respect to w. This guy. Okay, so that's something we'll see we can compute pretty easily. And now we need to find this down lambda star. Okay, so how do we find lambda star? So now we're going to pull out of the air another system of equations that turns out to have the same solution as lambda star. So for this, we start from, now we're going to be looking at this positive phase. Okay, the lambda star is going to be computed in the positive phase. And the positive phase is going to finish when we reach the fixed point where the derivative of the positive phase energy at plus with respect to the state is equal to 0. And that's going to define what S plus is. It's the place where we've converged to the fixed point in the positive phase. So now we can take this equality and we can differentiate with respect to beta, in particular the beta y. So that's just considering that this is a function of both S and beta. Okay, so now I'm going to do something maybe a little bit tricky mathematically, which is I'm going to think of the S that I care about here as the S that I end up at the end as a function of the particular choice of beta, right? Because the S that I'm going to get at the fixed point would have been slightly different if I had picked a slightly different beta. So I'm going to differentiate. I can consider the derivative of this thing with respect to S. We're going to differentiate the second time by differentiating with respect to beta, and then we're going to say, well, the differentiation with respect to S, I can decompose into differentiating with respect to beta, I can decompose into differentiate with respect to S, and then ds d beta. But then there's also a direct dependency of F plus with respect to beta, so I get this cross product of derivatives. All right. So now I have this equation, and let's see. We had defined F like this. So we're going to try to plug what these quantities represent. The second derivative of F plus, because of looking at this part is F minus, is just the second derivative of F minus with respect to S squared, plus beta y times the second derivative of C. So just taking this and taking second derivatives with respect to S everywhere. So that's going to be for this thing. For this cross derivative, well, that's going to be very easy because we take the derivative of this with respect to beta y. It's going to kill everything except the term beta y, and we just kind of cy. And then we take the derivative of cy with respect to s. So we get dcy ds. Okay, so that term is just dcy ds. Now we're going to do something else. We're going to consider the situation, because remember I said I'm going to just give a little nudge to the output units by picking a beta that's very close to 0, but positive. But basically, you know, we're interested in what happens when we take beta equal to 0 and we start moving it. We're going to move beta just like it. So at that point where beta equals 0 and we start moving it, the term in beta here is going to be 0, basically. Because that's going to be 0 or tiny. So this goes away. And now we can plug this into this equation, and we get d2f minus ds squared plus ds plus d beta plus dcy ds. And now we look at this equation and we recognize that it's the same as the equation we had for lambda star, except that we replaced lambda star by this funny ds plus d beta. And so now we know what lambda star should be. ds plus d beta, and what is that? So it's basically how the change in this coefficient, that is how much of a push we're giving on the output, influences the state of each of the neurons at the end of that positive phase relaxation. Okay, now we'll see we'll be able to do something with that. And we're almost done with the pain. So we're getting to the point where we're going to have gradients, because remember I said the weight change is going to be minus the Lagrange objective BW, and we have this product where this is something we'll see we can compute lambda star, and now I kind of know that it should be this derivative. Okay, so now that we have a formula for lambda star, we can plug it and see what we get. We just multiply these things by this thing, we get that. And now let's try to figure out what this term that I said was easy would be. So we have this equation for E. So we just plug. When we differentiate with respect to both S and W, we're going to get this. So first of all, let's just differentiate with respect to W. So when we look at this and we differentiate with respect to W, we get just rho of Si times rho of Sj, right? So we get this kind of term, but then we have the derivative with respect to S, so we have this kind of term. Now this is something that's starting to look interesting, because it looks a little bit like Hebbian things. In fact, we'll make the connection now to the STDP update, or next slide. But you see there's a product of pre and post synaptic activity here, and that's a funny rate of change. It's not time yet. It's how the whole state changes. Okay. So so where were we? We have this guy that we now figured is this thing, and we multiply by kind of ds d beta. Okay, so now we can see that there's a kind of chain rule going on here, and I'm putting some details on the right mathematically, but basically we have d something ds, ds d beta. So that's the same as d something d beta. All right, so now we have this guy. So what does it say? And we want to do this at beta equals 0. So, okay, so we're going to be changing beta from 0 slightly positive. And that's going to bring us into some configurations S plus. We start at S minus where beta equals 0. So this thing, this thing, which is the weight update now, okay? We now have a pretty simple formula. It says, take the Hebbian product, pre and post product, and see how it changes as a function of increasing the nudge on the outputs. And so basically, this would be, if you were to do a finite difference of this, right? It's the pre times post activity product after when I've reached beta equals some small value minus the pre times post before I've changed it. So that's when beta was 0, right? So that derivative is how the pre times post changes when I change beta. That means, I mean, up to a constant is just the difference between the value you get after I change beta by a tiny amount minus the value before. So we get this. And for people who know the literature in sort of theoretical neuroscience, this kind of thing, this is Hebbian, like positive Hebbian in the positive phase minus negative Hebbian in the negative phase is a very common thing we see. It's called contrastive Hebbian learning. It was proposed without this kind of justification in the early 80s and studied in the 90s. The main difference with contrastive Hebbian learning is that we are running this positive phase relaxation for only an incremental time using an incremental pressure to change the outputs. Right, so we're going to have a tiny trajectory. But otherwise, this looks very much like contrastive Hebbian learning. Yes?
What does beta y corresponds to in neural network?
What it corresponds to is how fast the output is driving the output units. I mean, the observations are driving the output units towards the observed values. That's all. So beta is just the pressure, it's a scalar that controls the pressure on the output units to move towards their target value. So so now we have this formula, the contrastive Hebbian thing, but remember, this is happening just a little bit after S minus, after we've applied this pressure. So let's consider integrating over that trajectory from t minus is a time when we are at the negative fixed point to t plus is a time when we are at the positive fixed point, and so we can basically say this is the integral of this product along the trajectory, which is basically going to be the difference. If you do the integral, it's just going to be the product at the end minus the product at the beginning. But now I've kind of something that has a d dt in there. And now I'm going to do a little bit of magic using a very trivial thing, which is the derivative of a product. So the derivative of a product is, differentiate the first thing times the second thing plus the first thing times the derivative of the second thing. So I can rewrite this guy, which looked like the contrastive Hebbian update, into something that looks like, for each synapse, now I have the pre and the post synapse, right? IJ and IJ here have a reverse role, where the pre-synaptic times the rate of change of the post-synaptic comes up, and here is the reverse. So what is it saying? It's saying that if somehow I was able to force these weights to keep their symmetry, and I don't know yet how to do that, then the sort of average update that I would get would correspond to the right gradient. So the contribution coming from the I to j link and the j to I link added together gives me the right gradient. And so, and if I were to look at what each individual update would be, it would be just the update rule I had at the beginning, this STDP update. Okay, so that was a long trip. And let's try to now summarize, and also I'm going to show you quickly some experimental results. So we're thinking about temporal derivatives of neurons as corresponding to error gradients. We're thinking of the feedback paths as computing incremental targets associated with the feed-forward path. So last year I proposed something called target propagation, where I was thinking that the feedback paths compute a full new target. And we have things like that in some of the algorithms, like we weighted wake sleep and variational autoencoders and the bidirectional Helmholtz machine. But here it's a bit different. We also have the feedback path that computes a kind of target, but it's an incremental target. It's a small change, just like in backprop. And then we have this idea that what's happening in this network is propagation of these perturbations, which correspond to some kind of surprise. Again, an idea that has been around in theoretical neuroscience for a long time. But now we're sort of linking, at least to some extent, to backprop. Okay, so I won't have time to go into details of the experiments, and there's a lot more detail in the paper, which you can find on arXiv. But essentially, what we're able to do using these negative phase relaxation and a very short positive phase relaxation, and then just doing updates, forcing the symmetry in the experiments to train an NMLP with feedback connections on MNIST in a reasonable number of epochs, like 10 to 25 epochs, and get 0% error on the training set. Now, so that's good. It's optimizing. For some reason, I don't really understand. The test error is pretty large, like 2%. But at least it's minimizing prediction error, right? So something good is happening, and the theory is not just totally crazy. At least we validate it in this way. All right. So in summary, what the paper was, these papers are about. First, that there is a form of update rule which has been studied before in the literature, based on rates, which seems to emulate STDP in simulations. Second, that and that's a theoretical paper that has no experiments, that propagation of perturbations at a fixed point of a symmetrically connected recurrent net propagates gradients. So that's just the fact that these deltas propagate and that they correspond to derivatives of the prediction error. And third, that's new, that this actually, if we combine these two things together and apply STDP with the symmetry constraint on the resulting changes coming from those perturbations being propagated, we get stochastic gradient descent. So that was the last part that I presented. And then the one last slide that I showed, but there's more detail in the paper, is that it actually works, that it trains neural nets. But these neural nets are different from the ones we usually train, because now they're more expensive because we have to do these fixed point relaxations for each input. And I could tell you a lot more about that, and there are lots of things we don't understand yet about these. But let me tell you more broadly what are some of the open questions that remain. We need to do a lot more with respect to the noise aspect. Like really, we would like to have a distribution that we're playing with rather than just a deterministic state. So maybe instead of thinking about a fixed point in the state, we want to think about a fixed point in the distribution over the state. I'm not sure yet how to handle that. Or maybe we just inject noise and don't worry about it. The other sort of, I think, even more fundamental question is, I'm not satisfied with the requirement of this analysis, of this theory, that we have to wait for the network to go to a fixed point given X. I don't think the brain can afford to wait that much, with maybe like 20 iterations going up and down, right? It's just there's not enough time. Things are moving too fast in the world around us. And so we need to have a learning rule that works even if we don't reach any fixed point. And my intuition about this is I think we can turn things around, and the same story about propagating perturbations that we've used for the output, we should be able to use for the input as well. Anyways, I'm not sure yet how this will be dealt with, but we have to get rid of the requirement that we need to converge to a fixed point before we can do an update, which is not biologically plausible anyways, and it's not machine learning interesting because we don't want to do all that computation. Also, we've only studied the supervised case, and of course, we really need to deal with the unsupervised case, and it's probably the most interesting one. We have to deal with the symmetry problem. And then the biggie is how do we extend this to a sequence of inputs, right? So this gives us some reasons to believe that something like backprop may be happening for a 100 millisecond interval during which you have one image coming to you. But you actually have a sequence of these 100 milliseconds moments, and backprop through time just doesn't make much sense from a point of view of biological implementation, because you would have to store the state of the whole system for all history, which doesn't make much sense. And maybe there are solutions, but right now I think it's pretty much an open problem. All right, I'm done, and thank you.
Yes. The energy term contains both the x and your label, right? So aren't you essentially learning the joint p of x comma label, or is it p of label given?
No, because if you look at what I'm actually minimizing with the update, it's really, given that I've planned x, now pay the price for the prediction error. Right. So on x, I'm not paying any price. I mean, I'm basically saying I'm going to just force the x to be the observed value, and I'm not trying to predict it. It doesn't matter what the prediction was. We should do the same thing for the input. We should allow the input to differ from the observed input values, and then it's basically trying to predict the input as well. But for that to work, we need to probably deal with the stochastic version. Because notice that the corresponding predictions here, I mean, depending on how the cost is structured, but probably independent predictions on the different units. Right? We don't want that. We know that that's not good enough for unsupervised learning. We need structured outputs or structured inputs sometimes. Yeah.
So it's dangerous for me to make an analogy between two things I don't really understand.
I do that all the time.
But well, one of the things that strikes me about this is it's intriguingly similar to some of Carl Friston's stuff. Are you familiar with this?
To some of his papers, yeah. So the idea of, the inference connection is something that he's worked on quite a bit.
Well, the multi-layer propagation of errors as well. Now the problem he's actually
but he doesn't have a credible story for that's kind of similar to backprop for the total learning.
No, the thing that's interesting is that the problem he's addressing is different. That what you're showing here could maybe address the problem as well, and that is that the y in his case is not like a desired input; it's more like a goal state that you want to achieve.
Sure.
And the x is the state of the world. And, and in his case, it's not just that you're changing your idea of what the world is; that you actually modify the world through action. So the propagate.
Okay, so he's dealing with the reinforcement learning problem.
What's that?
He's talking about the reinforcement learning problem.
Yes.
Yes, that's another bag of
very much like reduction of error between your prediction and your state. So in that sense, there's a similarity there, I think. But again, maybe it's
okay. Well, I need to look that more carefully.
It might be I don't know. It might be interesting because he tries to connect it to biology as well, but not back. But actually, I have another question. If I could just
sure.
The idea of this kind of you're implying there's a phase here between sort of perturbation and relaxation, Well,
I don't believe at all that's what brains do.
Okay, so you're that's more of a math.
For me, it's a stepping stone. I want to get rid of the relaxation on the negative phase as well.
So it's more of a mathematical way of getting at the math of what it's doing.
Yes. Yes. I don't believe that's plausible, and it's not good for machine learning either. But it's already something, right? So.
Just one question. Perhaps I'm out of the domain. Perhaps this comment is quite.
Sure.
So is there any connection between the structure that you assume for the energy function and the structure for the weights to be symmetric with the convexity of the energy function?
Well, so clearly the choices you make in the energy function have an impact on the symmetry issue. The convexity with respect to the weights, it's linear in the weights. You mean with respect to the state? I don't understand maybe what convexity you're talking about.
Because the energy function as a function of states, so
yes.
The structure that you consider, is it?
It's not convex here because of the rows being nonlinear. We have non-convex functions. These sigmoids-like things, they're non-convex.
So how does this gradient descent make sense then? Because
we don't worry about. In my field, we're very happy to do gradient descent in non-convex functions. It works really well. It's amazing. Yes.
So I'm wondering, because you talk about supervised learning here, and I'm wondering if that's just convenient to start doing experiments.
Yes. Not just experiments, theory.
Theory, yes. And then is there any?
And I would really love, to extend this to the unsupervised case, and I intend to, delve on that.
Is there any situation that you have in mind that you think would be make sense for the supervised learning picture?
For the unsupervised learning picture?
No, the supervised learning picture.
Well, yeah. So you actually have a current sequence of things that come to you, and then your brain is in a state that's roughly in agreement with what you've seen before. And then something new comes up. And then the interesting part is that there's a kind of adaptation of all the neurons to reflect that small change. And it turns out that this gives the right kind of information you need for gradient descent, for backprop.
Right.
And I think you could turn that on its head and do unsupervised learning with the same spirit.
I guess that example, it seems to be more like you don't have a y, but you have an x, and then x changes.
Yeah, that's right. You can think of, you have a sequence of x's, and the y is the next x. Yes, you could have something like that. Any other question? Well, thank you very much.